Okay, all right, so we are happy to have Raymond here with us. He joined LBL as a postdoc the beginning-ish of this year. Time means nothing these last couple of years, right? So here in person, it's usually based at CERN. So in town, we have a nice off-the-cuff hit meeting, so we can hear all about what we can learn about the quark-gluon plasma from reconstructed jets with Bayesian inference. So, off to you, Raymond.
Thank you. It's good to be here in person, I'm quite happy to be here. So as you just said, I will talk about what we can learn here. And so, I'm an experimentalist, so I at least think of this from kind of an experimentalist perspective. We have this huge collection of jet quenching measurements now from kind of an experimental perspective. So we can ask, we have all these, RIC and LHC, Phoenix Star, all the LHC experiments. We have all these different collections of, observables. What physics can we actually try and extract from it, and what kind of picture can we put together with this? And so, to draw kind of a very loose analogy with another approach, right? We can kind of think of a connection to multi-messenger astronomy here, right? Where we have this really beautiful image from the first gravitational wave that was confirmed with additional signals in the EM spectra, and they really have this very comprehensive picture that they can put together by taking this multi-messenger approach of observing many different phenomena and having different ways to constrain really this same event or the same phenomenon. So we can ask kind of, can we try and emulate this approach in our own way to really try and take all our measurements here and many more and build up a more coherent picture, right? So the three questions that I kind of want to think about today is, how can we actually try and make this consistent picture? What kind of physics can we try and extract from this? And also thinking, kind of a little bit forward-looking. How can future experiments maximize their impact in terms of what measurements they might be able to add and what information we might be able to extract from this. So, as might be guessed from the title, my answer to this is going kind of through a Bayesian direction. So, right, we can ask a question for a given model: what parameters are most consistent with, most compatible with our experimental data? And we can, if I frame my question in this way, it really is inherently kind of a Bayesian question. We can try and use Bayesian inference to extract our parameters that are most compatible with our data, combining our knowledge of both our theory and our experiment. So just as a little reminder of what we're trying to do here, how we go about doing this, right? We have for some data, some set of data X, whatever we might be interested in, and some model parameters theta, right? We can relate these with Bayes' theorem. So, right, the terms of interest here are our first one in blue, right, which is our likelihood that our data is described by our parameters. So this depends on the covariance of our data, so the relationship against uncertainties, our theory uncertainties. It packs all this information here. We have our prior distribution in this kind of purpley red that really makes our choices for our parameters very explicit, right? So we really need to make choices for what we're going to try and consider as our possibilities. And then we combine these together appropriately, and we get our posterior distribution, right, which is what we're really interested in. And this describes the probability that our parameters describe our data, right? So this is somehow our most probable, this corresponds to our most probable, the most probable values provide the best description of our data. And so this is what we're going to try and take advantage of. So slightly more practically, what does this actually look like? Well, at least what I will focus on today is really focusing, doing these analyses in the hard sector. And so that means we'll get to in a moment, but roughly we have some set of external parameters that we use to try and vary our model, which tends to be on the order of 5 or so. And so we have this whole n-dimensional phase space, parameter space that we need to try and explore and understand to be able to see what's compatible with our data. So we need to be able to populate this whole thing, but And in the ideal case, we just run our simulations throughout this whole parameter space. We could apply our normal Bayesian techniques, and we'll be all set. But unfortunately, right, our simulations are very, very expensive, and so this means that we can't quite take such a simple approach, right? So instead, what we need to do is we need to run our model in some subset of the state space, sampling it appropriately. We'll get to it a little bit more. Run it for the subset, and then we try and train some model to pervasive value. So in this case, we use this Gaussian process emulator, right, which gives us this non-parametric interpolation between our different points and gives us some uncertainties associated with that. So what we try and do here, right, we have basically our inputs, our experimental data, our model, and the parameters we're looking at. We take these, or with our first order model and our parameters, we train our Gaussian process, and we combine this with our experimental data to utilize some Markov chain Monte Carlo to then eventually get to our posterior distribution. Despite all these tricks we play, we're still talking about millions of core hours for the simulations of the subset that we look at. For our simulations, we've been running on some various facilities provided by Exceed. I will mention a little bit more about this later. But it's quite a process to produce. And so we're doing all this with JETSCAPE, so we of course have to have our requisite JETSCAPE framework slide. I hope this is familiar to folks, so I'll be pretty brief, but right, generally the idea here is we have this overall framework, right, which allows you to slot in, it's modular, so you can slot in different models for different particular regions and gives you an opportunity to extend or really make direct comparisons by swapping these in and out. And then in addition to our framework here, we also have these Bayesian statistical packages that obviously we're using to do these analyses. So okay, so that's kind of the broad setup. So kind of our first step in this process is looking at just inclusive charge hadron RAA. And so the idea here is that we really wanted to have something of a proof of concept. And so we, instead of trying to be very expansive, we really wanted to focus in on a single observable, just this inclusive hadron RAA. And we took just a subset of measurements. So we took measurements from our 3 square root S, including some central and semi-central, so that we try and expand our information a little bit, but really trying to focus on this particular piece and demonstrate our methods here. So for this first analysis, we have a comparison of a couple different models. What's the benefit of our approach here? So we look at LBT, we look at matter, and some early multi-stage model. Right, this is this approach that JETSCAPE uses to transition between different models and as a function of approach value, for example. And so we have this first early stage model with matter plus LBT as well. In general, for all these different models, we have them propagated through this same 2+1 dehydro with some pre-computed events. And then we need to try and figure out what parameter space we're actually going to explore to do these to perform this analysis. And so what we need to do here is what we need to do here is we need to somehow parameterize our real physics model according to some external parameters. We vary these parameters, move around in space, and we can use this to compare against our data to see if there are regions where we're able to describe it. And so for this analysis, we utilize this Q hat shown here that has 4 to 5 parameters, kind of depending on what model we're looking at. And roughly, it's kind of focused on 2 different terms here. So this term on the left is particularly focused on kind of high virtuality terms. So it has no temperature dependence. So it might expect, for example, matter to be more applicable in this region. And we have this HTL-like parameterization here that is scattering off some medium with temperature T, focusing a little bit on the lower virtuality region. And in the cases where we have, for example, this multi-stage approach, we have this explicit switch between these different terms. So to kind of just step through the idea here in terms of the analysis, the idea here is we first want to start with sampling our prior distribution. And so you can see here, we have our Hadron RAA data from Phoenix, Atlas, and CMS, these different square root S for 0 to 10% in the blue, kind of hard to see. You have to squint a little bit, but it's really there, as well as our semi-central in the red with our data points and their uncertainties. And so basically what we see here is that, at kind of a high level, we see generally that our model mostly envelopes kind of the data, meaning that the model in general should be able to kind of describe this, but so we cover this whole space, but we need to then try and go from our prior distributions here to then try and constrain them in more detail, or to constrain them using our Bayes' theorem. And if we do this for this particular model, we see a result that looks something like this. So now instead of looking at samples of the prior, we're looking at samples of the posterior distribution, again for the same data. And we see, we have these much stronger constraints. Now, you can stare at this for a while. There's a lot of information you can try and pick out, but I'll point to a few things. So kind of in general, the data seems to do, or the model seems to do reasonably well at describing the data. But if you start looking closely, you'll realize that there are some regions of tension. So for example, kind of the semi-central here, as well as we go into the 5TE, you start to see some tension. You can also see that, you can also pick out that it's not just from the model side, but also from the data side, there can really be some important details here. So, right, in the case of the RIC data that we're comparing against, there are some quite large uncertainties, and that has some impact on our ability to kind of constrain this data, which I'll show you more explicitly in a moment. So, by looking already at these kind of distributions, we can already start to extract some information and kind of understand what's going on here. So, kind of the next step is if you're sufficiently convinced that your model does a reasonable job in constraining your data by looking at the posterior distributions, then you can then try and turn around and look at the actual distributions in terms of your parameters from your Q hat. We have a kind of cartoon of here, and so we have our individual and joint distributions are shown here. And so going along the diagonal, right, we have basically the single dependence of the particular parameters, and we have the correlations here with matter in the blue and LBT in the red. And so you can stare at this for a long time, and there's a lot of information that you can pick out. I will just highlight a few things. So one, if you look at both the distributions for A and for C, you'll see that that in general matter seems to prefer A, and LBC seems to prefer C. And in fact, that you see this kind of strong anti-correlation between the two parameters. And so if you go back then to our parameterization, as I kind of hinted at before, you see that these different models seem to prefer the different terms, with matter preferring this kind of high virtuality term, and LBT preferring this HCl-like term. And so really what you see here is the parameters that we're these parameters that we've used for our Q-hat parameterization seem to really, what's picked out reflects the features of this parameterization that we've put in. Now we can go from just these individual models to also look at this multi-stage, this matter plus LBT, where we do this transition. And we can pick out some more here. So you'll notice that we've added a new parameter, right? We've seen this transition parameter Q. And so in general, this is not what I'm showing, or I don't show this directly here, but by comparing the posteriors, for example, we see that the multi-stage doesn't yet appear to do any better at describing data. It does fine, but it doesn't step up our ability to describe the data. We see that it transitions kind of around this 2 GeV with some width of the distribution. But what we can pick out here is that if we look at the constraints comparing now LHC in the blue versus the combined in the red here, and this RIC curve, which is in green, which is only shown on the diagonal, we see that almost all the constraints are driven by the LHC data, right? And this is a different way of basically representing what I pointed out before, that these large uncertainties from the Hadron RAA at RIC really limit the information that we can actually extract in terms of the model here. Now, of course, we should be a little bit careful, because if we go back to that plot for a moment, you'll see that we cut off at some 9-ish GeV, right? And of course the data goes a little bit lower. So we have to address this with some care, both in terms of basically where our model's applicable, right? If we constrain to an area that's not applicable, we might not be picking up a meaningful constraint. But also, if there's small uncertainty data here that we can use and we can take advantage of, right, that may improve the constraints, and the weaker constraints here may matter less. Alternatively, as I'll get to in a moment, we also have a lot of incoming future data that will help us out in this direction.
Can I just comment?
Yeah.
So in all this variance here, apparently they said LLC can really provide a lot of constraint, but still, well, especially if you only look at some of the parameters, essentially distribution is flat, which means that it really cannot constrain the parameter, right?
Right.
Talk about the on the diagram.
Yeah.
The green here, right? Yeah.
It's only essentially there is no constraint.
Right. So that's right. I wanted to point. You're exactly right. I just wanted to point out that this is a little bit of choice, right? We stopped at this point. There is smaller uncertainty data to the side, but the model applicability may be partially an issue here. So this is where, for this analysis, where we're kind of proof of concepting, this is where we focus. But
so what would happen if you cut off at 16 and above for a week? I mean, there the error bars don't look much worse than the LHC.
Sorry, 16 and above.
Yeah, you get rid of this.
Oh, so I don't think this is the particular issue. I think it's just the overall size of the uncertainties here. It's
well,
that
that's not much worse than what I see on the LHC. I'm sorry.
These uncertainties are quite small.
Many more points.
Yeah.
That's fair enough. That's
Relative
fair
precision of. So, but I think there's I don't want to steal Raymond's thunder, but I think there's a very important principle with any of these analyses is that the data, the precision of the data is very, very heterogeneous. You can have very precise data. In particular, I think, you're going to get to this later, or
What, the hadron versus
kind of
jet?
the precision of hadron versus jet.
Yeah, I mean, I'll get there, but
Let me
it's
just
fun.
so
Go ahead.
the hadron data is actually much more precise than jet data. From the experimental side, on the theory side, you may prefer the jet data to the hadron data. I think there's kind of a choice or a balance.
It depends on which theory you ask.
Exactly. So there's I think what this exposes. I mean, it's intrinsic in everything we've collected for the last 20 years. It exposes how each measurement is sensitive to underlying physics. Do you prefer very precise data that requires more theory manipulation, or what do you prefer?
So let me ask another stupid. I'm totally ignorant about this whole business. So your fitting procedure, or AKA Bayesian analysis, the fact that, and I look at the middle plot.
Right, okay.
The fact that you go through this small data on the left with the small error bars and very dense, is that an effect of the fitting procedure because they push you much harder than the few points to the right, and that's why you see the tension there?
Yeah, exactly. So these points of these small uncertainties, they're very
they control your fit much more than everything else.
But as does the theory has a functional form.
Right.
Well, I mean, I would say from this, the theory sucks because you don't get anything at the end.
Talk to the guy sitting behind you.
So therefore, if the theory sucks, I throw out all these analyses because I have the wrong theory where I fit my data.
Okay, Volker just gave the right conclusion. You can stop now.
Let me also say, this one I kind of picked out because we did this for a number of models. I picked these out because it's easy to kind of point at these. A lot of them, do quite a good job describing it. This is not exactly the typical one, but I think it's the one worth thinking about.
So can you back to your formula again?
Yeah, if my mouse is not moving now. Yeah.
So maybe it's not a real legit question. I mean, we know that this is something which we parameterize to fit the data.
Right.
I mean, of course, the theory support that. People derived this formula many years ago. Can we just have very, very kind of, how to say, neural network kind of approach? So I just have some energy energy dependence, which we don't know, right? And then we just go fit the data. Then the data tells us what that is.
Right. So I think it's a little bit of a trade-off, right? Because say you just had some incredibly general description, right? I then extract some parameters, but then how do I make sense of them? right? How can I actually interpret them, right? It's just I have some coefficients that describe the data, right? So there's some balance. I mean, I think this is definitely a thing worth thinking about, right? Because as you kind of balance back and forth about how interpretable it is versus how well you describe the data, I think there are different directions you can go. But it's I think a little bit of a trade-off in that sense.
Well, that's the point of our research work. We use the so-called field,
Right.
Information field theory, where you don't specify a functional form. Yeah, and then all you need is the correlation lines, for example. You make sure you don't have strong correlation in your prior between very low temperature and between very high temperature. That's all you need to know. And we actually concluded that if you only have include weak data, you have it does not provide much constraint on QHAT, not overall, but still there is a certain region of temperature. Actually, it's sort of like bottleneck, and there is a precise constraint.
Right. Yeah.
So even if you don't use any parameterized form.
Yeah.
So the constraint it cannot constrain this is only in certain region, but some region you still can provide some constraint, especially at low temperature.
Yeah, you're absolutely right. I maybe undersold that a little bit. Yeah. Agreed.
That was just a famous point. I mean, I tend to agree with Raymond. I mean, if you can do a completely bias-free, theory light parameterization of the data, and then what you've done is you've parameterized the data. And then what? Right? I mean, ideally one wants to start from the QC to the Lagrangian and some theory of what the plasma is made up of, and come up with a functional form and say, does this work? Doesn't work? Let's see what's missing.
So what I'm trying to get here is that with neural network PDF, they did a global analysis of current distribution functions, right?
But there's DGLAP. I mean, there is QCD content.
Yeah, of course.
DGLAP is the essence of it.
No. What I'm trying to say is that you get the PDF from that phase. And then what do you get from, if you follow the same logic, you get QHAT as functions say E and T. And then from what data tells you, then we can go ahead to some QCD. So for example, the PDF does tell you, for example, how it behaves with small x, how it behaves with large x, which we can learn some QCD.
But again, these PDFs fits, they must be based on DGLAP, which is where QCD comes in.
Yeah.
So this is, I kind of think of this as sort of the equivalent of DGLAP. It's a functional form. You kind of don't know some of the basic parameters.
No. What I'm trying to say here, QHAT is what you use to describe the data. You do have your QCD formula how to describe the data, right? So QHAT is some kind of functional form or some parameter in your understanding of the spectrum, right? Depends on temperature, depends on energy. I mean, of course, you do have QCD model, right? You can have QCD calculation. Engineer have his calculation, somebody else have their calculations. I'm just saying that what actually data tells me about this function. And maybe you don't get anything from that. I don't know. This is my question.
Yeah, okay. I think maybe I'm having a little disconnect in kind of following what you're trying to say. I think I don't think we're falling far necessarily, but I mean, I think you can try and generalize the sum, and we do, in fact, for kind of our next analysis. But I think still there's a balance a little bit of what you can extract versus what you include. Still, you have your model choices, and how well they can actually describe the shapes.
But I think if I could just follow up, if I understand the question right, it's basically to what extent do I care about A, B, C, D, and to what extent do I just care about QHAT?
Right.
I think that they're different questions. Right? If I just want to compute QHAT and compare it to like a lattice calculation or something, then I can use it.
Okay.
If I want to understand like a perturbative calculation of A, B, C, E, then
You do need A, B, C, D.
That's right. Yeah. Definitely. Yeah. Thanks. Okay. Right, we talked about all this. Okay. And quite appropriately, okay, we get to QHAT here. So we translate all the parameters back we do some analysis details, and we get our Q hat, shown here for as a function of temperature. And so there's still a lot going on here, but I'll just highlight a couple of things. So one being that, right, we have our posterior distributions here for the 3 different models that we have compared here, shown compared against our prior distribution, in this case for our multi-stage model. And already you can see that we have some significant constraints in our posterior distribution based on what we've extracted here. You can see also that we have we're approximately consistent with this previous extractions from the JET collaborations. This is all very good. We kind of match up some with our expectations there. And we have this continuous distribution between RIC and LHC. Again, the caveat of our selection of the RIC data. We also see that this multi-stage model is kind of consistent with these other 2. But as I said, it seems to be fine, but doesn't get us too far ahead yet for this first analysis. Right. So we've kind of proved our concept here, and we're reasonably confident we can work with this. So there are many ways you can go. The direction that we've gone for our next step is to add our inclusive JET RAA data in addition to our hadron RAA data. And so okay, so right, we're doing this new analysis. We need to do some model selection here, and so for this case, for this analysis I'm going to show today, we're using basically a new multi-stage formulation of this matter plus LBT, which has coherence effects at high virtuality. And so somehow we have some scale evolution of the constituents, which basically is encompassed in this kind of effective jet quenching term. And kind of in practice, what this means is that as you go to high Q squared, you have somewhat reduced interactions compared to as you approach 1. And as you get down then to when we transition to the LBT phase, we've basically reduced down to this HTL formulation. So there's a lot more details in this paper here that's now in the archive that goes through kind of all the formulation of this, but I'm going to be pretty brief here. This time we have our partons propagated again through our 2+1 dihydro, but this time using parameters that have been calibrated by a Bayesian analysis. So we're improving our description in that. Okay, I will just show the results from here today, but I want to emphasize, right, we're kind of taking this as a potential candidate model, but again, the benefit of having this JETSCAPE framework is that we can switch pieces in and out. And so this is something that we want to continue to look at to take advantage of. So, right, as important as our model selection is, we also need to decide what data we're actually going to include. And right, in that first analysis, we were trying to kind of make sure we were in control of what we're doing, but now we want to try and be as inclusive as possible, right? We, you want to take all your data and you only want to exclude something if you have a really, really very good reason to do so. And 2 experimental instruments disagreeing with each other isn't a good reason, right? You want to take all the data at kind of at face value. So for the analysis that I'll show today, this is the list of what we've included. So we have JETs and hadron RAA, both from RIC and LHC, over these different square roots here. We have some variations in JET-R, for example. It's not quite comprehensive, but our aim is to be comprehensive. So this is a little bit of a consequence of kind of when we did this work in progress analysis, which I'm showing here. But as we converge to kind of a final analysis, we will include really absolutely everything that's available. So briefly, so we have these pieces. We can kind of just go ahead and run our analysis again. But briefly, I want to do an interlude just to highlight some of the details of kind of what this involves, right? Because frequently we just go from the previous slide to jumping to our prior and then our posterior, and there's a lot of details that this all hides. It takes really a lot of preparation, it takes a lot of organization to actually make all this happen. Just briefly, right, so we have to choose our model, we have to choose our parameterization, which I've already mentioned. We have to set up our computing, we have to steer this, we have to support it, make sure it all works. For example, in our particular calculation, again, now trying to run millions and millions of core hours, we're split across different facilities, so we need to deal with kind of all the computing technical aspects. We need to actually set up and validate all of our different, for example, observable calculations, right? There's quite some variation when you really get into all the experimental details. So one wants to be efficient and careful. You need to do quite some checks and work to try and do this. You need to define your simulation parameters in terms of kind of how you sample your n-dimensional parameter space. One piece that we've taken advantage, or one new tool that we've taken advantage of is utilizing so-called active learning. So basically trying to, once you have a block of points, instead of just continuing to kind of space them evenly in this n-dimensional space, instead what you try and do is you look at points, you look through the phase space and try to find areas where your uncertainties are largest in terms of your kind of understanding what the model will look like there. And you focus your points in these places, which then lets you both try and converge kind of more efficiently and reduce your overall uncertainties. So you have techniques like this. And then once you've done all that, you still need to actually submit your jobs, monitor, make sure everything runs. So this is some a test of our monitoring, and it gives it really an overall view of kind of how these jobs run. But instead of 12, replace that with 2,000. And to highlight, I don't want you to actually be able to read this, but this is kind of a very high-level overview of just the simulations we've run in the last couple of months, and it's just this tremendous effort, right? So you need to make sure everything really fits pieces, and it's really a truly collaborative effort. So I want to acknowledge all my colleagues and all the effort that everyone's put into actually making this happen. So
I stumbled over your first step, choose your model. I mean, the gravitational wave guys, I hope they don't choose a model. They know what to calculate, right? So what do you mean by choose your model?
What I mean is, we've made a choice to use matter plus LBT for this particular analysis we're looking at, right? We can try and predict these pieces. We can switch out matter, switch out LBT, for example. But in this particular case, we've made a choice, right? We're comparing it against this model with the previous one, right? We chose these different ones we're looking at.
Isn't Dan Kaysen writing a model?
Yeah.
He's writing a model?
No, but not the guys who observe the gravitation.
Oh, they do. They have so-called template.
The ringing?
Each
But this is
template.
run by
that's not a
computational
model.
gravity.
Yeah, each template. I mean, in this case, general relativity is considered a theory, right?
Exactly.
They use that to.
They don't have
Calculate
20
each
20 different models.
So don't you have to conjecture equations? I mean, if you want to extract the equation of state from the ringing, you need a model of the
No,
equation of
that's
state.
another,
Well, but that's, if you want, I think the analogy, at least in my mind, maybe I got this wrong. You want to take gravitational wave data,
Okay.
you want to extract the equation, the equation of state,
Okay,
a neutron
fair
star,
enough,
and you want a
fair
neutron star,
No,
you
fair
need a model for that and how that modifies the ringing. So I think that's directly analogous.
Sorry, isn't the equation of state just an afterthought for the gravitational waves?
You want a neutron star merger? I can tell you about the
Isn't
wave.
that just an assumption about the size and the mass that counts? Not the actual equation of state. Can be simplified to a density versus volume.
I think the way it rings is a dynamical thing. There's
Well,
one
I'm not
more
sure,
information.
I'm asking.
Anyway,
Right. Okay. So I did my slide to highlight all our efforts here, but now I'm going to do my jump. So we can look at our prior first here for our work in progress distribution or analysis. This is really only a very small subset of data that we've now simulated, but this is kind of what we've taken a look at. And so, kind of as a high-level thing, we've changed some details here, but the overall analysis is quite similar to the previous. The procedure, at least, is quite similar to the previous one. But we need to be a little bit more careful this time because we have additional we need to deal with some new sets of experimental uncertainties, for example. So by introducing JETS, right, we now have, for example, new sources of systematic uncertainties, such as shape uncertainty, which is anti-correlated, right? So I'm not going to go through every single piece, but the point is, once you have this, you have uncertainty, you have multiple measurements from the same experiment or competing experiments. You need to try and understand how different shared experimental uncertainties propagate. You have to take account of all these different pieces. So I'm going to gloss over all the details here, except to highlight one particular piece to our experimental colleagues, which is to say, ideally, if you really want to try and do a precise extraction, having the full covariance for the uncertainties is really best, the gold standard. But at the very least, trying to do kind of assigned uncertainties can already be a big help in trying to understand these different correlations. So with that, okay, we have our power distribution. It roughly envelopes our data here. And we can then do our next step and try and do our calibration and look at our posterior distribution. And this is what we have on the right here. So as a reminder, of course, this posterior is we're simultaneously constraining by all these different observables here across our square root S and our different experiments. There's a lot of information here. If you start this for a really long time, I would broadly characterize it as the model describes many of the observables reasonably well, but there definitely are some regions of tension. Now, it's very hard to stare at this from here, so I'm going to go through some details to try and kind of guide your eye here. So we can first start by kind of focusing on just as a function of square root S. And so we have a couple different break observables, right? We have our hadron RA as well as our jet RA. And again, we see somewhat similar message to our previous analysis in that our constraining power is still somewhat limited due to being in this high PT range. We are grabbing some additional information with these jets, right? But we still have these constraints. One of the things that we're kind of in process of doing or would like to look at is trying to expand these ranges, kind of as I mentioned earlier, to try and include some stronger constraints here. We can look then at 2.76 TeV, and broadly our message is the same, is that we're kind of mostly consistent with the data, but there is starting to show some tension, particularly, for example, this high PT RAA here between our posterior and our data. It's not terribly significant yet, but you're starting to see some kind of hints. And then we get to our 5 TeV data, and this is where we start to see really some stronger tension, particularly between the hadron and the jet RAA. And for example, you can look here, you can see that we're really, as you go to high PT, for example, it tends to really somehow, the posterior tends to really underpredict our data.
So wait a minute, so what upstairs is hadrons and
So yeah, so here, these are the two hadron RAA, and then these are all jet RAA for different R from different experiments, from Alice and CNS. So we can break this down a little bit differently because this is still kind of a lot to stare at. So one way we can try and break this down is basically looking at a single hadron and a single jet RAA as a function of square root S. So top we have 200 GeV, middle is 2.76, and bottom is 5 TeV.
So Raymond,
Yes.
just for, I don't know if this is a good place or maybe you discussed it. How was your analysis of JETSCAPE or the Bayesian analysis calibrated with respect to cloud
Honestly, calibrated.
uncertainties?
That's what I was gonna ask, and like the PP and stuff like that. Those like global uncertainties that come into these sorts of.
How many nucleons, binary collisions producing a hard scattering you have in, in the model
Right. So the way we
to extract RAA?
Right. So the way that we run these calculations is right. You end up simulating jet by jet, and then your centrality is basically set by the hydro events you're putting this into. So
Or I think for the jet production, you have some end-goal distribution probably. You
It's
scale
not
by.
being fit, like, everything is fixed except for some
It's not fixed.
parameters that
Did you say it's
show.
not fixed?
It's fixed according to some modules. Only the jet evolution.
So yeah,
But the data.
I guess I would go one step further, that you probably want to have the Bayesian analysis of things like, T and dieta as a function of centrality, right? To see how well you model, and then tune that part, and then go for RAA, which essentially may produce some vertical uncertainties. Right?
What are you talking about? You are asking that to a global constraint both on soft sector and high BD sector. Is that what you want?
Principle, yes.
Yeah.
It's a collision. Right? But then we look at RAA and say, oh, RAA is off by something. And then it's like, Is it
Well, this is-
physics?
No,
Is
so
it
this, I think in this case,
Is it
it's
simple?
the hydro they
Sure.
use,
Yeah.
has been tuned already to that.
Yeah, it's
Basically
calibrated.
it's basically factorized.
It's separate, it's separate, they assume that the bulk part will not be influenced by a single jet.
No, but it's not just the ballpark, to produce RAA, you need to know how many nucleons collide on average.
That's based on the, in that model, they use a global model
So that's what I'm
with a
asking, how
transient
the,
initial condition.
how the Glauber model was calculated.
Which is,
Using this
yeah,
the end
fantastic infrastructure,
You could also say, okay, let's constrain our encode, right, for those central
that,
data.
that's been taken care of.
So, but then I think your question, that question should be asked of literally any
Yeah,
jet calculation. Yeah, I mean, one could generalize, but just to keep the problem tractable, we factorize it. There's someone else in JETSCAPE, Chun Chen and others calibrated the soft sector, we just take that, and there's an assumption implicit, and Shin already said, that the jet propagation isn't changing that in any
that
way.
I buy, that's fine, that's
So,
fine.
so then we take the
Distribution
calibrated
of
item.
hard-scattering sentences, something, okay, fine. So,
It's the same question you should ask for every calculation, but point taken.
No, I'm confused. So this RAA is experiment data, right?
The data, in Kenyan's calculation, you have to.
no, what is 10% central? What experiment claims is 10% central? How do you model that in the model?
So you need some model initial condition.
Okay.
What if they take 8% and,
So it could be wrong in
But
the
the data
calculation,
is
and that would be responsible for some of the tension.
But yeah, I mean, your point is well taken. I will, in fact, on this slide,
But it can't be wrong as a function of PT, right? It can't be, correct for low
But
PT
then
and
your
wrong for
tension
high PT.
appears elsewhere, right? That's what my point is, that then your tension appears elsewhere.
Well, I think this shows already that low PT is okay, high PT is off.
Unless it has
Right,
a shift,
unless there's a
right?
shift and low PT is off.
because there is a global uncertainty
It's a
on this,
problem.
right?
It's a problem,
Okay, good.
it's a problem, then your tension shifts into a different region.
Yeah, but isn't that the reason, because you have much more point and better points at low PT, that's why the fit works. I mean, your fit gets driven to where you have the most
Yeah.
translation, right?
That's a separate,
No, but that, all right, I mean,
no, that's a separate.
But the agnostic statement is the model taken as a totality, the jet propagation, the Glauber calculation, everything is not, the functional form is not
right,
represented
that's,
today. That's the
that's what you
agnostic
can say,
statement.
but you cannot say the model works at low PT and doesn't work at high PT, you cannot say that, because if you have only more points at high PT, then all of a sudden your fit goes there, right? I mean, that,
That's
That's-
fair.
That too, that was.
No, this has, I think, this has nothing to do with how you model the soft power.
No, it's a different,
It's
it's a
different.
different issue.
This essentially is how the model within this JETSCAPE,
Now it's a feature of.
how the jet is evolving with PT and so forth. Okay, there's tension there, which means tell you the model somehow is not perfect.
yes,
But I claim you don't know where the tension is.
exactly.
And I think
No, I
Volker
agree.
also says you don't know where the tension is.
But you can make an exercise and take less points at low PT and make artificially the error bars large and see where your model goes, right? I mean, and then you
right, yeah, certainly. I mean, you can do that, right? So yeah, I mean, exactly what you
So
said, right?
there's theory is discarding the data, there.
well, that's definitely still learn. If you want to learn something, don't believe in the
I
data.
understand, it was a joke.
No, I think it's.
I agree
No, but
with you.
I'll phrase it in a.
No, I agree with, I know what he wants to say.
No, but I think it's, you can ask, do I get the same parameters if I restrict my data
Right.
here
Yes.
or here? That's a legitimate question to ask.
Yes.
And clearly we get a different answer.
Yeah, I mean, yeah, so the point that I was gonna highlight here, which, okay, we've already kind of gotten to, right, is it seems that at least within this set of constraints that we have right now that we're looking at, it seems that really there seems to be some tension between, we have these very low PT points in the Hadron RAA that seem to be driving our analysis that somehow seem to have some tension with our jet data.
Sorry, I'm still confused. RAA, the data is coming from experiments. Do they also have to calculate the number of the collisions?
Absolutely.
This question doesn't really, I mean, it's not your JETSCAPE problem, it's an overall problem.
Well, there's always, experiment always provides an error bar on the TAA. That's always part of the what's reported. Intrinsic to inclusive.
So do you also JETSCAPE also reproduce the numbers?
That was
I guess the
spirit of my
RR
question.
must include the TA, well, it's fine here. The central position got to be done.
Then I don't understand Mathieu's question. I mean, so basically you reproduce what the experiment give you TAA. I mean,
Well, I don't know, that was my question.
Yeah,
Do they tune the nuclear overlap such that it corresponds to what the experiment does,
but that's what they say they do.
Okay, I mean, here is what I do, okay. In experiments, you select centrality according to your, either your ET distribution or multiplicity distribution. And that we do in hydro.
Right.
We feed that, and then in this case, you have a selection or range of either impact parameter or just selection of events.
Yeah.
And those events are in your centrality selection.
Right.
And within this, each event, you count the number of binary scattering, unless you divide it with.
I think that
but still there's an interesting question. But
we've been studying this lava for 20 years or more.
Yeah.
I actually think that for central collisions, I don't say this easily. If you look at different correlations, different pieces of phase space, you look at lava, how well it does. I think it's under pretty good control. My strong suspicion, I think all these comments are good. My strong suspicion is this tension is not due to mismodeling the geometry. It's got a different origin.
So here's another stupid question.
except there's more to geometry than just number of collisions.
Before I have to leave. So suppose I have a model where which actually is perfectly fine because God-given dynamics at high PT. But it sort of fails because at low PT I need extra corrections. And now I put this model in, and of course there are a few parameters. Now I have a lot of precision data at low PT, so I squeeze the model which actually works at high PT into a box because at low PT it fails, and all of a sudden I get nonsense. To say it bluntly, right?
Yeah.
So how do you make sure that this doesn't happen?
Yeah, I mean, so this is I mean, kind of a little bit of danger. I was talking about this in terms of like direct data, right? We have some cutoff at some particular range where we think the model is valid, right? If you went further, you could constrain to very precise data that may be in a region you're just modeling.
What I'm trying to say is your precise data might actually hurt you.
So the solution, I think is to put the theory uncertainties in the likelihood.
Then it would be
If you
have them under control.
Well, that's your problem.
Not mine, genius.
Right? I mean, it's not just the experiment that's uncertain, it's the theory that's uncertain. And if you can quantify the theory uncertainties, then this is an unbiased, then that'll fix your problem.
Exactly. Good. Sorry, I have to go now. Nice talk.
So the last way we can kind of look at this, just to kind of take some interest here, is as a kind of fixed jet R at a fixed squared S. So basically kind of comparing the different experimental measurements here, right? Because perhaps there's some tension in these higher PD points. And so what we see here is that it seems to kind of suggest that the posterior really seems to prefer these low, these kind of small uncertainty points from Atlas, right? Which is exactly the point. You need to kind of be aware of the uncertainty of your data. So one other thing that I kind of wanted to highlight here is something we're kind of thinking about some more is kind of how you handle these different observables and their different precision. Peter already mentioned this a little bit, right? But the idea here is that, right, if you have different experimental observables, they might have different inherent precision, right? Our hadron RAA, for example, in some regions are really, very, very precise. But you may have different information content contained in these different observables, right? So, for example, maybe your less precise data may contain kind of more information or complementary information that you don't have otherwise. Maybe it's better theoretically justified, right? It could be all these different kind of classes of questions, but you might want to figure out kind of how you optimize these different pieces. How do you, particularly given that, right? If I look at, say, my uncertainties here for my hadron RAA, right? My uncertainties in this posterior, again, only part of our statistics for our simulations, but you see that our kind of the width of our posterior is more comparable to the uncertainties of our data. Whereas at least in some cases, kind of the size of the uncertainties of my jets is generally larger than my posterior distribution here for what we sampled, right? So you have kind of a mismatch between the uncertainties that you're kind of able to get with the same set of simulation parameters, right? I can of course tune my simulation to increase my hadron statistics, but I might be trading off my dynamic range for my jet measurements, at least within some particular set of computational resources. Right. So the question is, how can you try and kind of optimize these different competing constraints? How do I optimize my competing resources to best extract the information that I'm interested in with the consideration of more or less precise observables? I don't actually have an answer for this yet. We're just starting to think about it, but it's an issue that we've kind of been grappling with. My hope, my expectation is that we're not the only folks that have tried to deal with this. So I think certainly something of interest is to try and look at what other fields that utilize Bayesian inference might be able to tell us about this type of problem.
And also they're different. The single inclusive hadron versus a jet, they do have different physics, additional physics. If you only look at single inclusive jet, essentially it's the energy loss. But if you only look at jet, it's both energy loss, evolution, and also medium response. They all play a role there. So that's why when you do this simultaneous fit, you do have actual physics comes in that you don't know.
Right. Right. Yeah. Exactly. So okay. So kind of summarizing back up here. It's been a very nice discussion. So we can then stare at our overall posterity distribution again. There's a lot of information here. We can spend quite some time thinking about this and staring at it. I've only shown you this work in progress. There's still a lot to go here, but I think at least it demonstrates the interest that we have in kind of how we can take advantage of this. So for my last part here, I'm running out of time. I'll try and be quick. It is thinking a little bit about maximizing the impact of future measurements. So the idea basically being here, right? I'm using this nice plot from James and Ehlers, for example, right? We have all these different models that, generally speaking, do quite well at describing our data, despite the fact that they have these different formulations of kind of the underlying physics. And so, if we want to try and kind of make some more quantitative statements, right? We want to take advantage of this Bayesian analysis, which means we want to be able to include new measurements. So thinking, for example, at future measurements or future experiments, right, from, for example, high luminosity star in S Phoenix, right, which is just coming up, or LHC run 3 and 4. All this is going to be quite critical. But there's another question we can kind of think of a little bit, which is to ask, can the Bayesian analysis ideas here that I've shown, can they try and provide us some information before we even get to this era? Can they inform what we might want to try and do? And so the concept that I want to just introduce here to think about is this idea of Bayesian sensitivity quantification. So the idea is basically trying to ask, what is the impact of new data on the existing analysis that you've done? And so this is not like it's not a new idea. It's not it's been applied in many other places. For example, in neutrino physics, or for example, looking at oxygen projections with tridectum. So this is a well-known idea, but I think it can be really quite nice. So the idea is, what you want to try and do is you first do your initial calibration. So analysis that I just showed, for example, you get some calibrated model, for example, ours, or from our first analysis, right? Then what you want to try and do is you take the posterior distribution, you say, here are my parameters that I expect are most probable, and you want to generate some pseudo data using those parameters, and you set your expected uncertainties to, say, in the case of a future experiment, what your projections are, or data you've already collected for whatever observable you might be interested in. It could be some new substructure observable, or it could.
No, I didn't finish your
Okay.
sentence. I
Okay.
just want to say something.
Yeah. Right. It could be some new observable, or it could just be kind of asking, what do I want to prioritize with my new experiment for things, say, for example, going to higher TT at RIC.
So a related comment to what Volker was mentioning, this generating pseudo data, you can use the existing data,
right,
and artificially decrease the uncertainty of high PT.
Right.
Right. This would be equivalent of moving the weight from low PT to high PT.
Yeah. This is
And
exactly
today, right? Systematic.
Yeah, you could. I mean, if your data still isn't gonna.
Instead of Volker's proposal, let's cut completely the low PT.
Right, yeah, you could, exactly.
Reweigh them, you can reweigh them in your uncertainties.
This is exactly the idea, yeah. And so, right, however you wanna do it, you try and, get some new values that are reduced, these small uncertainties that you project out. And then you can try and rerun your Bayesian inference, now including this right, in the case of the pseudodata, what's nice is at least you're kind of on your model, which gives you kind of a baseline, right? If the value shifted, now you have, you could have some even larger impact, but at least gives you kind of a baseline of what kind of constraints you might see. And so you run this new inference and you compare, right? You add in your new data, you run your new analysis, and then you get some further constraints. And so you can ask, trying to do my just JET-RA at high PT at RIC, is that really what's going to make the big difference? Or will my next measurement, looking in a fragmentation function or something else, can this, is this really the direction I want to go in terms of being able to try and have high impact? So there's a lot of different directions you can go with this, but I think it's something useful, particularly to keep in mind as we get better at these calibrations, particularly in the hard sector. I think it can be quite a useful tool. Okay, so with that, I come to my conclusion, and I think I'm really out of time, so I'll be very brief. I hope I've convinced you at least a little bit. I think there's really a lot of power in these Bayesian inference tools. Really trying to think of this kind of multi-messenger type paradigm and utilizing our heavy ion data. I think I've shown you things with JETSCAPE, but I think this really can kind of apply more broadly, particularly thinking about these projections, for example. How do we have the resources to really be able to do this more broadly? It's quite computationally expensive. I think these are all things worth thinking about. My last highlights here, I'll repeat this again. I hope I have a receptive audience, but the more we can report about uncertainties experimentally, I think it really will make a big difference in how we can understand what we're doing. There might be some interest in trying to do these sensitivity studies. In terms of the JETSCAPE side, right, we've got to finish up this analysis where we've put a lot of work into running all the simulations and really understanding what we're doing. And then we can try and do exactly these things, right? Trying to study the consistency of our data points. If we include some range, does that have some impact on our parameters? Trying to ask all those kind of questions. And then of course trying to feed this back and use whatever constraints we're going to find to then advance our field forward. With that, okay, I want to just flash the faces of the JETSCAPE collaborators because this is a tremendous amount of work, and I'm talking about these things, but so many people have contributed. Thanks. Are you not in there?
No. I'm there.
Everywhere.
What I missed is that at the end you did this combined fit, like a single hadron and single JET-RA.
Right.
Versus the earlier work that there is only single hadron, right?
Right.
So do you have some kind of comparison of the final extracted Q height, the comparison of these two?
Not yet. So I intentionally kind of stopped short on this analysis because this is what we showed at Quark Matter, and we've run like a factor of 5 more in simulations exploring this parameter space and what have you, but we haven't quite gotten to the point where we've extracted the parameters in kind of a reliable way. So this is still in progress.
Yeah, I mean, this is related to what I commented earlier, because by including single inclusive jet, you also have to bring in extra new physics, medium response, jet evolution, and it is very important to see whether by including this single inclusive jet in your analysis, whether you're gaining more information.
Yeah, I fully agree.
Versus single inclusive hadrons.
Yeah, I'm very, very excited to see what comes out of this.
I'm
it's
too.
just it's been a big effort.
It's the question that's been countless person years of effort in figuring out how to measure and analyze jets and heavy ion collisions. And the question is, what have we learned? What have we learned? What does that add to the hadron measurements, which were already measured at RIC 20 years ago?
Second comment. I mean, as an outsider, I look at this numbers, I think pretty good, okay? Only one or two plots is some tension, right? But like what Shania said, that this may be some new physics we have to learn from there. But in general, I think both parts, I think we have a very nice picture, I think.
I'll take that as a negative comment, because I would hope for, I want to break the theory. I want to find new things.
You got it, that's the two.
You got it, in the middle of the two quad.
Yeah,
Okay, I like those, I like those.
You like those, but still, think about it, the bulk part, you got it right.
Yeah,
And there's still some detail.
but there's this vast wealth, I mean, Raymond already flashed this, slide of, gallery of stuff, there's this vast wealth of jet data, we are just getting started. Inclusive jets are just the first thing, there's any kind of, gamma jet, there is substructure. I mean, those are the main, there's a vast bodies of data, and, the theory, there's good, basis for theory on both directions. What happens when we start adding those?
That's true.
But we gotta go very slowly, really emphatically, otherwise you get lost.
Very good, very good. Anyway, I'm just comment that this, when we did this single inclusive hadron using this information field approach, we also include dihadron, gamma hadron.
Right.
And then in the beginning, we thought, oh, this by including dihadron and gamma hadron, which are more sensitive to the Q hat, then we would have gained much more information. And that's what we hoped. And then our estimate is also true. That's the case.
Right.
But then once you take into account the data with large error bar, few data points, it turns out it does not really add much information because the error bar is so big for dihadron, gamma hadron.
Yeah. Yeah. Also, the other thing I will add here is thanks to a lot of work from James, a few others, that right, we have a ton of observables calculated beyond this, right? So things always take longer than planned, I suppose, but I think there's a lot of ways we can go with this, and a lot of observables we can try and add and look at. So I'm excited to see where that goes.
Especially for single inclusive hadron, I think it should be easy to. The simulation is there, the vendor there. All you have to do is to analyze dihadron correlation.
So yeah, what I'm saying is we already in fact have the histograms with the dihadron correlations, for example. Like it's all sitting there. Just
which is most sensitive to the Q hat. Unfortunately, our experience tells us that because the large error bar you have, it does not really do much extra, provide you much extra information.
Right.
Well, I mean, that's important to know. I mean, it's as Raymond said, it can guide the experimental. I mean, as Phoenix is planning to run, and Raymond gave talk at this Phoenix meeting a couple months ago, and Star's going to run. Ehlers is starting up. Where do we need to focus?
Yeah, definitely. You should ask maybe anybody.
Yeah, so far, nobody online. Anybody have any questions before we wrap up? I'm gonna take silence as a no. In that case, if nobody else in the room has it. Let's thank Raymond again.
Very good.
Thanks, everybody.
Thank you.